So good afternoon, everyone. My name is Amanda Pierce, and I'm the current chair of the Farvolden Day Committee. And I have the opportunity here to welcome you to the 29th annual Farvolden Day, which I think might be the hottest on record. So I just wanted to start with thanking those companies who've sponsored the Farvolden Day activities today. So thank you very much for that. Great, let's give them a round of applause. Great, and then before we start with this afternoon's agenda, it's important that we acknowledge where we are today on the traditional territory of the neutral Anishinaabe and Haudenosaunee peoples. In the last few years, I've had the opportunity to work in an Indigenous community, and through that work, I've come to learn the importance of taking a moment to acknowledge the Indigenous peoples' lands where we work and live, and the actions that we can take, especially as groundwater scientists, towards reconciliation, including an openness to learning about water resources and those peoples who have been using those resources for thousands of years. Preserving our groundwater resources was especially important to Bob Farvolden. I did not have the opportunity to know Bob Farvolden personally, but through my work with John Cherry and Beth Parker, I have learned that science is a multi-generational collaboration, and along with everyone in this room, we are part of the legacy Bob Farvolden established here at the University of Waterloo. So prior to arriving at the University of Waterloo, Bob Farvolden was the founding director of the hydrogeology group at the Alberta Research Council and a member of the hydrogeology research group at the Maxey University Reno, Nevada Desert Research Institute. He made his way to the University of Waterloo in 1967, where he was tasked with providing direction to a fledgling Earth Sciences department and brought together a critical mass of hydrogeologies that has led to world-class research. So in speaking, as I prepared for this introduction today to Bob Farvolden, I spoke to those who knew him. Bob Farvolden emphasized how important the physical hydrogeology system is to all groundwater problems and encouraged curiosity-driven research and fostering collaboration in hydrogeology research. So it's nice that we can gather today and celebrate Bob Farvolden and his legacy. So with that, the day started this morning. So we started with a student mentorship and networking session. So this included 13 organizations participated, and we kind of did a speed dating type of interview student mentorship networking event. And then the Farvolden Day events will continue this afternoon with Dr. Clare Robinson giving us as our guest speaker, and then as well as a reception afterwards. So we hope everyone will take a moment to stay around. So I just want to take a moment to say thank you to the 2024 Farvolden Day committee members who I've listed here. And these members of the Farvolden Day committee helped to organize the student mentorship event and adjudicate the applicants for the Farvolden Day scholarship. So a big thank you to everyone on this year's committee. And especially, I would take a moment to thank Sue Fisher for helping to organize the student mentoring event and provide us and gather all the Farvolden Day scholarship applications. And then especially to Lorraine Albrecht, who without this event really would not come together. So a few reminders before we get going. Remember to fill out your ballot for the door prize. So hopefully everybody had an opportunity to do that or will. And then also that the lecture will be recorded, but not the question period. So please don't hold back on your questions for Claire. Okay, and with that, I'm going to give the floor to Chris Hauser, the Dean of Science.
Good afternoon, everyone. As introduced, my name is Chris Hauser. I'm the Dean of Science here at the University of Waterloo, as well as a professor in the Department of Earth and Environmental Science. On behalf of the Faculty of Science, I would like to welcome Dr. Clare Robinson to the University of Waterloo to give the annual Farvolden Lecture. I would also like to thank everyone in this room for their continued support of the Department of Earth and Environmental Sciences and the 2020 Endowment Fund. Through the 2020 Endowment Fund, we aim to ensure that future generations of geoscientists have the training they will need to solve our most complex problems. Your support of the fund will provide new equipment for labs and fieldwork, greater access to teaching assistants to help to prepare our students for success, and support for vital field trips and field courses. In support of our students and the 2020 fund, the Faculty of Science has made a commitment to increasing the number and diversity of high-impact learning experiences for our students, from the hydrology of the rainforests of Costa Rica to groundwater exploration here in Ontario. So as a geoscientist, you know that the most important thing that we can do is get our hands dirty in the field. We are committed to increasing these field opportunities, and your support will sustain and enhance that growth. Thank you, and again, welcome to Dr. Robinson.
Okay, thanks very much, Chris, and I'll echo that on department's behalf. Thanks so much for coming out to the event. That's the reason why we have this, and it's so great to see everybody here. I bring regrets from Mario Canelio, who can't make it today, so he's got me as the fill-in. Sorry about that, but that's what we get. And I've got the departmental update for you. So it's been a big year for us in so many ways. Lots of change, lots of exciting things have been going on. I want to share some of that with you today. So I'm going to cover sort of the department in numbers like we normally do. Some of them are quite revealing and interesting to look at. We're going to present a concept of a new graduate program that we've been thinking about and developing and really reaching out for feedback from everybody on this. And Randy Stotler, who's the lead, will be sharing the details of that with us. Then it's been a remarkable year for awards. I want to go through some of those with you. We've had some interesting retirements and starting to get into hires, so there's lots of transition going on in the department. I know that's of interest to most folks. And then I'm going to cover some of our plans, challenges, what we're looking at for the upcoming year, and move into the scholarship. So, department by the numbers. First of all, I would say that these numbers are relatively stable. So, total number of faculty members. There's a second line there called teaching stream faculty, and that's a new term for us. So, this was the lecturers and continuing lecturers, and the university has now made a special stream, faculty stream for our lecturers, which is about time. So we're delighted to be able to say that we've got a group in there. An area that's growing fast are postdocs. So our research has been making space for postdocs in the community, in our group, and it's gone up substantially over the last 3 years. Other numbers are about the same. So those are sort of the big changes. This one we'll see is about to change. So what about our student enrollment? And this is one that we've talked about every year, one of the things that keeps us awake at night, and how to attract the next generation of students into the geosciences. And we've certainly discussed the fact that all throughout North America, I would say, in Australia, that Claire could probably tell us about, and in Europe, number of students entering the geosciences at different levels has gone down. And for reasons we're not 100% sure why, but things have stabilized to some degree. Interestingly, the environmental sciences program continues to be popular and continues to grow. So that has two main streams, geoscience and water, two streams students can enter. There's one other stream that comes in with environmental sciences, and that's ecology. It runs through biology. So that's a very big feeder for us. Our earth sciences, the classic ones that you can think of, geology, hydrogeology, geophysics, has been going down a bit over the years. That's a concern for us. Not exactly sure why. One of the areas that has really been going up has been geological engineering. And part of this, I think, is due to how the outreach has been going, and we're working on that. But it's been a really successful year. We've had a really big incoming group in geological engineering, which is super exciting. In terms of our graduate students, we're probably, from the historical highs we've had, we're relatively lower numbers of graduate students these days, again, for a variety of reasons, and I'll get back to that in a little bit more granular detail in a moment here. So the undergrads, if you look back over time, in terms of earth sciences, it's been relatively stable. And of course, we're hoping to increase that That's what we're really working on in terms of recruitment. And I was just speaking to the dean just before we started here, and getting into the high schools, getting into the early high schools is probably one of the best ways for us to do that. So we're looking at ways of getting it at grade 10 rather than grade 12 when all the decisions have already been made. So we're looking at different alternatives there. And I mentioned we've had just passing, when we came out of the pandemic, when everything went down, we've had a nice ramp up in geological engineering. So pretty excited about that. Graduate then, let's look at the enrollments there. One of the areas that we were always very, very powerful in was in the master's world, the MSc world, and that's gone down significantly. Again, we're not 100% sure why. And interestingly, we had, and thanks for this, we had 13 companies come today to meet our students. It's clear from the calls we get all the time and the number of people that are coming out looking for students that there's a great market for the geoscience students. And it's something we have to promote that because there's such a need in society for our graduates, and we're really, really wanting to focus on that. PhD incoming has been fairly stable. So overall, our numbers have maybe not as high as we're hoping to. That's a concern point and one we're working on. So one of the ways we're thinking of doing this, the university is really encouraging all operations to consider opening online and shorter-term master's programs, course-based. And we've got one that we're developing here in Earth Sciences. It's becoming mature now. It's coming along. And I'd like to invite Randy Stotler to come up and give you an outline of that. It's really, really exciting. Randy. Thanks.
Okay, thanks, Dave. Okay, so as Dave mentioned, we are working tirelessly here to try to come up with new ideas and new ways to, I guess, provide students to the workforce. And one of this is this new applied geoscience master's degree program. And this program is going to be reaching out to different cohorts of students than what we typically have tried to attract here. This is going to be primarily an online program. There's going to be 1 or 2 residential sessions where students will come here, have the opportunity to network, get hands-on field experience and that sort of thing. But really, we're targeting people who may not be able to come to Waterloo for whatever reason. Maybe they're working or living somewhere else in a foreign country and can't come here. While obviously, we'll still be able to work with students here at the university. Like I said, we're trying to make this primarily online. There will be multiple streams and specializations for this. They're going to be very well defined, so it's not going to be kind of like our current course-based master's program where students can come in and take, they could take a course in sedimentology and one in hydrogeology and structural geology and kind of mishmash a whole bunch of things together to create a degree. Rather, this is going to be a very focused degree. And it can work as a full-time or part-time course. There will still be a capstone experience with this. It's not going to be a thesis. It's probably going to be a project or an internship type of opportunity. The final point on this slide you'll see is that we would like this to be guided by an industrial advisory board. So we're trying to make sure that the people that we're producing have the skills that are needed by the workforce. And so that's going to be kind of a primary focus of the program. The initial program that we are going to be working on is going to be hydrogeology. Again, there will be other programs to come in the future, and this is just kind of our early concept of some of the types of courses and concepts that people will be working on. We've been working with Waterloo alum Ty Foray, who's at the University of Arizona. He's doing a lot of work right now, working on exactly what are the curricular needs for hydrogeology. What is the knowledge base that we need? I'm also interested in what are the soft skills that we need. Do we expect everybody to come out of here with a master's degree that is able to write a report, for instance, those kinds of things. At the same time, we're also working with micro-credentials. So the idea behind this is maybe somebody's not ready to come all the way and get a full degree. And so they'll have the opportunity to take some shorter-term courses. These could be over the course of a weekend or over a couple of weeks. This will be a mix of different existing courses, part of the new program. They could also be kind of standalone types of things. So let's see here. And so finally, as always, I'd love to have your feedback. I unfortunately will not be able to attend the reception this afternoon. I've got to teach class at 2:30. So if you'd like, you can click on take a photo of the QR code and reach out to me if you have any interest in being a part of, learning more about the Industrial Advisory Board, seeing what we're going to do with that. You can definitely reach out to me as well. And I thank you for your time.
So I think we'll just email this out to everybody on the Farvolden list, and Randy's really serious. Getting input from you right now is the best time we can get it. So please don't hold back, using Amanda's term there. Okay, so just the last few things before we get into the formal part of the show. As I mentioned, this year was pretty special in terms of awards, and I just want to go through a few of them here with you. Is Steve here? Maybe not. So Steve Evans, in fact, I need 2 slides for it this year, which is kind of exciting. Steve almost needed one on his own. So he won the Schuster Medal, which is with the Association of Environmental Engineering Geologists and Canadian Geotechnical Society. He also was awarded the E.B. Barrell Jr. Award from the GSA, published the Paper of Excellence with the Canadian Dam Association, and the Best Paper in Engineering Geology Award through Elsevier. So just a remarkable year for Steve Evans. Another remarkable year, I think Nandita's here. There she is. Nandita won the Joanne Simpson Medal. She became an AGU Fellow and also delivered the Witherspoon Lecture, which is a very special event at AGU, an award through the hydrology session. David Blows was awarded a University Research Chair, as was Chris Yakimchuk. Chris is here with us. And also an early Geological Career Award through the GSA. Philippe Van Capellen, I'm not sure if Philippe's here, but was awarded a very prestigious university professorship. Very excited about that. Carol, who's here, Carol became a fellow through the International Association of Geochemistry this year. Janine McCutcheon was awarded the Young Scientists Award, Mineralogy Association of Canada, and our Jane Lang Excellence Teaching Award within our own department. Gillian May, I'm not sure if Gillian's here with us now, won the Jim Duge Award, European Geosciences Union. I was very grateful to get a graduate student supervisory award. And Ramon Aravena, who's been retired for a long time, still winning awards, won a very prestigious International Association of Geochemists Award, the Verendeschi Medal, and also a Brazilian Groundwater Award for all his work throughout the Latin American world that we're all very familiar with. So in terms of change, as you may have heard, we've got lots of retirements imminent and have happened, and others coming up soon. So Maurice Dussault, Steve Evans, Sherry Schiff, Tony Enders, and Marianne Vandergrant have all retired or are retiring this year. And if you happen to be anywhere near the university on Friday, November 29th, we're having a celebration of careers for them. So please drop in. It's just going to be at the University Club. Everybody's welcome. Please join us for that. And you can tell by this picture that everybody seems happy. So I think they're onto something, eh? So I better think about that. Okay. And a really exciting thing, although we've had lots of retirements, we've had a great new recent hire. So we're really happy to announce that Colby Steelman has agreed to join the faculty. Colby's here, put your hand up. I know everybody pretty well knows Colby, but if not, we're welcoming him into this in environmental geophysics and hydrogeology. So really great to have him here. So last 2 things, what are our priorities coming up? Obviously, we're in the middle of strategic planning. So we're taking this machine apart and trying to figure out how to move forward on it. It's been really exciting, and it's really coming along. Part of that will be strategic hiring. And you can lean on the dean when you see him here, if he's still here. Is he still here? To say that we really need to hire people in the department. We're looking, as I mentioned, about strengthening enrollments, obviously a big thing for us. Making sure that we're maintaining our research program. It's been great. Funding's been going well. You can see that people are winning awards and doing really well. And as Randy pointed out, we're looking at more online offerings. So quite a few courses are coming online. Keith Delaney has produced some incredible ones. We're having hundreds and hundreds of people sign up for them. So we think that that's an area that we want to continue to develop in. Okay, so now let's transition into our scholarship. And I'll just mention the endowment for a moment here. We're hoping as we go into the 30th delivery of this next year, that we'd like to have more than one scholarship. We'd like to have one at the MSc level and one at the PhD level. So we're looking to expand the endowment. So if you're at all interested in donating, this is a good one. It's going to go to scholarships. It really goes to great use, and we're so thankful to have it. And to get the Farvolden Scholarship going, I'll invite Jeff Melchin up to the podium.
Great, thanks, Dave. Good afternoon, everyone. My name is Jeff Melchin, and I'm a member of the Farvolden Lecture Organizing Committee, and I'm also an alumni of the Hydrogeology program here at UW. And today it's my pleasure to introduce the Farvolden Scholarship. So just a little bit about the scholarship. It's awarded annually to a graduate student studying hydrogeology, especially where they are conducting research pertaining to the protection, management, or sustainability of groundwater resources for drinking water security or ecosystem health. This includes innovative research on aspects of groundwater quantity or quality, and where the research demonstrates benefits for communities and their residents. And so this year we had a great group of applicants who are completing a wide range of different types of research related to groundwater and advancing groundwater science. And so at this time, I'd like to call up Carol Ptacek to announce the recipient of this year's scholarship.
So I'm very pleased to announce the winner of the scholarship. And I actually didn't know Bob Farvolden, so I think Bob Farvolden would be definitely approve of this recipient. So the winner is Matthew Erdelski. And just Matthew, is Matthew here? There, yes, you can come down. Work your way down. So Matthew did his Bachelor's of Science degree in Environmental Sciences here at the University of Waterloo, and he specialized in water sciences. And also Matthew worked 3 work terms, co-op work terms from our group, and so that's why I know Matthew very well. He's an excellent worker, and I think is definitely very deserving of this award, this scholarship.
Thank you so much, Carol.
So if you could summarize your work.
Absolutely. Thank you so much. I appreciate that introduction, Carol. So thank you all for being here today. I am honored to accept this Farvolden Scholarship, and I'm grateful to the Department of Earth and Environmental Sciences for this recognition. This award holds special significance not only because of its prestigious history, but also due to its namesake, Dr. Robert Farvolden. His legacy in hydrologic education at the University of Waterloo continues to inspire us. Dr. Farvolden's contributions laid the groundwork for many of the advancements we see in groundwater research today. His leadership as a chair of the Department of Earth and Environmental Sciences, and later as a dean of the Faculty of Science, set a standard of excellence and dedication that we strive to uphold. My ongoing research project, the geochemical characterization of abandoned gold mine tailings, focuses on the potential for resource recovery and environmental remediation by analyzing gold mine tailings with high levels of dissolved arsenic. By identifying valuable metals within these tailings and assessing their impact on groundwater quality, this research aims to turn environmental liabilities into valuable resources. We are exploring innovative recovery techniques to help mitigate contamination while harnessing critical metals for industrial applications. This work is particularly timely given the Canadian provincial government's priorities for resource development to meet the energy transition demands. Abandoned mine tailings are often viewed as environmental hazards due to their potential to contaminate groundwater and affect ecosystem health. However, my research looks at these tailings from a different perspective. I aim to demonstrate that these environmental liabilities can be transformed into valuable assets with the right approach. By recovering metals from tailings, we not only reduce the concentration of harmful contaminants, but also provide essential materials for various industrial applications. In conclusion, this scholarship not only aids my academic journey, but also aligns with the broader goal of sustainable development and environmental stewardship. I am excited to continue this work and contribute to the legacy of impactful research at the University of Waterloo. Thank you once again for this incredible honor. Thank you so much, Jeff. Thank you.
Thank you, Matthew.
Yeah, absolutely.
And I did mention he's actually a graduate student in our research group. David Blows and myself are the co-supervisors. So we do look forward to this extra support for Matthew.
Escape.
Escape. Control tab. Alt tab.
One there, and then you see the presenter up at the bottom. There you go.
Okay.
Thanks.
Hello, I'm Michelle Fraser. I'm a hydrogeologist and a technical discipline leader for water resources at Stantec. I've been on the Farvolden committee for about 5 years now, and today I have the pleasure of introducing our 2024 Farvolden lecturer, Dr. Clare Robinson. Clare Robinson is the Canada Research Chair in Water Quality and a professor in civil and environmental engineering at Western University. Before joining Western in 2009, she received her undergrad and doctorate in environmental engineering at the University of Queensland in Australia. She completed her postdoctoral fellowship at École Polytechnique de Lausanne in Switzerland. She co-directs the Restore Research Group, which conducts innovative research aimed at addressing sustainable management of our water resources, as well as training the next generation with the skills needed to address pertinent water resources and water quality challenges. Dr. Robinson is an expert at combining field investigation with modeling to understand groundwater and surface water interactions in streams, lakes, and oceans, as well as the fate of contaminants in natural and engineered systems. Dr. Robinson received an Early Research Award from the Ontario government in 2012 and was a member of the International Joint Commission Great Lakes Science Advisory Board from 2014 to 2019. In her spare time, Dr. Robinson has probably swam, biked, and run a lot more than us in this room. She's completed 2 Ironman triathlons. For those of you that don't know what an Ironman triathlon is it's a 4-kilometer swim, a 180-kilometer bike ride, followed by a full marathon, a 42-kilometer run. I'll let those distances sink in, because that's about the distance from this podium to Detroit City. Not only that, but she has also qualified for and competed in the World Championship for the half Ironman distance, so quite impressive. But today with Dr. Robinson, we get to explore the impact of groundwater on surface water quality in the Great Lakes Basin at multiple scales. So please join me in welcoming Dr. Robinson to the stage.
So thank you for that introduction. I will say I did Ironman triathlon before I had children, and now really, I don't know, the children are more than any of, cycling and running to Detroit. So firstly, I'd really just like to thank the committee for inviting me here today to provide the Farvolden lecture. It's a real privilege and honour, to come to share with you the work that my research team has been doing in recent years, trying to look at and understand the contribution of groundwater on surface water quality. So when Dave first invited me to be the Farvolden lecturer, in the summer, he suggested that I look at some of the recent Farvolden lectures which are online. And I did that, and what very rapidly struck me was, one, how distinguished the previous lecturers were, but secondly, how a lot of the lecturers in recent years, or the ones at least online, all had personal connections or some personal anecdote that they were able to share about their experience with Bob Farvolden. Unfortunately, as Michelle said, or maybe fortunately, because Australia is a nice place, but I did my graduate studies in Australia, and so I wasn't fortunate enough to meet Bob Farvolden and really experience what people talk about, his incredible enthusiasm and leadership. So I thought, well, I've been invited by the committee to be the Farvolden lecturer, but how am I linked to Bob Farvolden? Maybe there's something here that they know that I don't know. So I know that myself, other than kind of recent collaborations I've had with the University of Waterloo, I didn't meet him, I don't have any collaborations on paper or with the colleagues that worked when he was here at the University of Waterloo. I thought, well, let me look at my academic ancestry. So my academic father, Dr. Ling Lee, who was my PhD supervisor, no connections on paper. And then I thought, well, my academic grandfather, there's got to be something here. No connections. My academic great-grandfather, Yves Palange, who was a North American academic. We're getting close to Waterloo here. There's got to be something. There was nothing on paper. There might have been things that I didn't know. So then I had to dig a little deeper. And what I realized was, as briefly mentioned earlier, was that Bob Farvolden was actually at Western University, where I currently am, for a very brief period back in the 1960s, before the University of Waterloo attracted him and invited him to set up the Centre of Groundwater Research and Teaching here. So, really, perhaps, me being invited to be the Farvolden lecturer today was really a consolation prize to Western, to say, sorry, you blew it. You let Bob Farvolden slip through your fingers, but, you know, all these years later, we're going to throw you the Farvolden lecture. So I do appreciate this consolation prize. What I did also realize is that I'm standing in a room full of hydrogeologists. And so really, if we think that, you know, Bob Farvolden was at Western in the 1960s, I arrived in 2009, so there's a 40-year gap, but if we think about this on geological timescales and the uncertainty in geological timescales, really, we could say that Bob Farvolden and myself walked the corridors of Western at the same time. So there we have it. I had my link, and I could actually get on with preparing my lecture. Honestly, though, what I did really realize, you know, through pondering this question, was that all of us sitting in the room here today, whether we're groundwater scientists, researchers, practitioners, or we just dabble a little bit in groundwater, we're all intrinsically linked back to Bob Farvolden. Because as the previous speakers have said today, really, you know, as a visionary leader in groundwater hydrology and contaminant hydrogeology, the leadership he provided and what he enabled at the University of Waterloo really sets the foundations for a lot of what we still do today. And so I think I reflect on myself, and while as a graduate student I didn't meet Bob Farvolden, really I was sitting there all the way in Australia at my desk, tearing my hair out and scratching my head, trying to learn these theories, these field techniques, these numerical modelling approach, the importance of three-dimensional flow systems, that was coming out of the incredible research from the University of Waterloo. And I think that's really a tribute to him, kind of highlighting the international reach that he had. So with all that being said, I can kind of move on, and I'm really delighted to be standing here today. And considering, you know, his international reach, that's why I'm so humbled and honoured to be here providing this lecture today. So I'm going to move on to something that I really like to talk about, and that's the Great Lakes and the water quality in the Great Lakes. So as I'm sure you know, everyone in the room is aware, the Great Lakes are an incredibly important freshwater resource globally. They're also really important for the economy, for the social well-being, for the environment of the over 30 million people that live in the Great Lakes Basin. With so many people, though, living in the basin, it means that the Great Lakes are exposed to a lot of human pressures, and with that comes environmental challenges such as water quality challenges. So there's not often, you know, a couple of weeks that go by in the news, particularly during the summer, where we're seeing, you know, the different water quality challenges in the Great Lakes. Whether it's, for instance, you know, high nutrient loading, in particular phosphorus, leading to the proliferation of algal blooms and in some instances hypoxic dead zones. Whether it's you want to go to the beach on a Saturday and there's a beach swimming water quality advisory because of high E. coli concentrations. There's also concerns about the salinization of the lakes because of the road salt applications. as well as, increasing concerns about these emerging contaminants and what are they going to mean for the long-term integrity of the Great Lakes ecosystems. But these water quality challenges aren't just in the Great Lakes themselves, but also in the tributaries, in the rivers and the streams that drain into the Great Lakes. So what does this have to do with groundwater? So we know that when managers are faced with trying to mitigate against these surface water quality challenges, we have to, for effective management and policy decisions to be made, we have to understand not only the land sources, so where are these contaminants coming from? Are they anthropogenic or human-derived? Are they geogenic, naturally occurring? We need to understand their impacts on the receiving water body and what that means for ecosystem and human health. But in between these two end members, we also need to understand how they're being transported from the source to where they have an impact. So we need to understand the pathways. Is it surface water? Is it groundwater? What are the travel times? And what transformations of those contaminants are occurring as they move from source to where they're having an impact? So for the Great Lakes, it's well known that surface water or tributary inputs are a major contributor of contaminants into the Great Lakes. But beyond this, we also know that direct groundwater discharge or groundwater discharge into the streams and the rivers is also a really important component of the water that's flowing in these tributaries. And this was shown, back almost over 20 years ago now, where it was shown that up to 42% of the total inflows into the Great Lakes come from groundwater. So this means, and there's other studies, for instance, in Lake Michigan, showing that groundwater may be accounting for around 70% of the total inflows into the lakes. So just by thinking about this, of course, with groundwater being such an important part of the inflows, the water quality of that groundwater really matters on the ultimate surface water quality in the Great Lakes. In addition to indirect groundwater discharge, we also have direct groundwater discharge. So there's a lot more uncertainty about how important direct groundwater discharge is for the water balance for the lakes, but this doesn't mean it's not important, because with everything groundwater, there's obviously a lot of heterogeneities. So in some areas, you can have disproportionately high groundwater discharge rates, or these hotspot areas of groundwater discharge, similar to what you can have with indirect groundwater discharge. And when these align with areas where you've got, groundwater contaminant sources, such as leaky sewers, landfills, septic systems, which often you see these areas along, the Great Lakes shorelines. You've got the GTA, Hamilton, you've got all these communities or coastal communities that use septic systems. It means that this direct groundwater discharge can be important in delivering those contaminants directly into the lakes. And particularly more so in ocean environments, this has been shown that particularly in embayed areas, it can have an impact on the nearshore water quality. So understanding the role of groundwater in delivering these contaminants into the surface waters is not important just because of the magnitude or the amount of contaminants being delivered into the tributaries and directly into the lake, but it's also really important because the groundwater pathway represents, a really major legacy contaminant problem. Because of the slow-moving groundwater pathways, it means it can take decades or thousands of years from when that contaminant first recharges into the subsurface to when it ultimately discharges into a surface water body. And we have to be able to understand these timescales to be able to effectively manage the surface water quality problems, because you have to have realistic expectations about how long it's going to take between when, for instance, you implement a best management practice to reduce groundwater contamination and when you're ultimately going to see improvements in the surface water quality. So although kind of what I've been talking about so far really focuses on, the direct and the indirect groundwater discharge as a source of contaminants into the tributaries, into the lakes, we also have to really keep in mind that groundwater discharge is also really important for improving the quality of the surface water in some areas. So in a lot of areas around the Great Lakes Basin, the surface water quality is, the groundwater quality is actually better than the surface water quality. So groundwater discharge can improve surface water quality in some areas. And groundwater discharge also plays an important role in ensuring the availability and the quality of aquatic habitats as well. But we have to be able to understand where is groundwater discharge improving surface water quality and where is it impairing the surface water quality, because they're two very different ends of the spectrum. So the importance of groundwater on water quality in the Great Lakes has been recognised really at the highest kind of government levels. And this is kind of illustrated through the Great Lakes Water Quality Agreement. Where back in 2012, it was probably a bit of a landmark moment for groundwater because they added a new annex into the Great Lakes Water Quality Agreement, which was a groundwater annex. And this was recognising its importance on the Great Lakes water quality and also kind of committing the federal, Canadian and US governments to coordinating on the groundwater science and the management actions. Since this time, there have been a number of different reports that have been come out to looking at summarising groundwater science in the Great Lakes Basin and identifying, the science and the management needs. Despite this kind of inclusion and recognition of groundwater for Great Lakes water quality, however, you still see reports like statements such as in the report here. So this is a US Geological Survey report for the Great Lakes back in 2021, so just a few years ago, summarising data and science needs. And you can see it says the extent to which groundwater quantity and quality affect the overall function of the Great Lakes system is currently unknown. And this is a pretty consistent type of statement that you see around groundwater. There's just so much uncertainty and kind of lack of understanding of how groundwater is really influencing the Great Lakes ecosystem. And I'd say I've been in Canada now for 16 years, and I feel like although we're incrementally moving the bar and improving our understanding of the groundwater impacts on surface water quality, it's been very incremental. And so we're still continuously seeing these types of statements. So, when it comes to understanding the influence of groundwater on water quality in the Great Lakes, there's a lot of different challenges and reasons why we still have this uncertainty. One of them is that groundwater is invisible, it's unseen, groundwater discharge, and so there's often this out of sight, out of mind mentality. There's also kind of this general notion in freshwater management that groundwater, it is difficult to quantify, and it's also expensive compared to, for instance, going down to a tributary and taking a stream water sample, analysing it. Whereas, groundwater, you've got to be putting in wells, you've got to be using, much more extensive techniques to measure it. With groundwater discharge as well, there's also a lot of heterogeneity in the groundwater flows and in the contaminant concentrations in that groundwater discharge. So this complexity in the contaminant kind of discharge from groundwater into the surface waters, combined with its invisibility, really compound to kind of add to this lack of understanding of the importance of groundwater on surface water quality. One of the other reasons why it's challenging to quantify the contribution of groundwater contaminants on surface water quality is that even if you do have groundwater wells that are located kind of distant to the stream or distant to the lake, when those groundwater contaminants are moving along their groundwater travel pathways to the surface water body, they have to pass through a reaction zone. So in streams, it's a hyporeic zone. In lakes, we have, for direct groundwater discharge, we have a similar kind of reaction zone. And so these reaction zones can ultimately govern how much of the contaminant actually discharges. And this makes it really complicated because these processes are happening at small scales, and it makes it really complicated to actually, quantify how much contaminant inputs are coming from groundwater into the surface water systems. So this means that we need to have multi-scale approaches, from kind of large regional scale approaches to small scale approaches, to be able to quantify the contribution of indirect and direct groundwater discharge on the surface water quality. So today I'm going to touch on 3 different kind of areas that to provide you a snapshot of some of the work that we've been doing over the last few years on this topic. Before I start, I'd just like to acknowledge my main collaborators for this work. One of them is Jim Roy, who's an Environment Climate Change Canada and also an adjunct at Western, and he's really played an instrumental role in particular the second two research areas I'm going to talk about today, in both supervising the graduate students and kind of helping direct the research as well. I'd also like to acknowledge Chris Power, who's a professor alongside myself at Western. We co-direct the Restore Research Group, and among other things, he's a hydrogeophysicist. So he's really opened my eyes to kind of the benefits of using geophysics as like a preliminary site screening tool, characterization tool, and using time-lapse geophysical methods to kind of track contaminants in the subsurface. So in addition, I'd also like to thank other faculty members who have contributed to the work, as well as, probably most importantly, the grad students who are really the ones doing all the hard work day in, day out, while I just stand up here and, get all the credit. So in addition to that, finally just acknowledge particularly the government agencies who supported my work in recent years, in particular Ontario Minister of Environment, Conservation and Parks, who have really played an instrumental role in setting the motivation for a lot of the research in my group, as well as kind of helping transfer the science we're doing to the government and to the end users. So, kind of moving on to the first topic I want to talk to you about today. This is some work that we did up in Lake Simcoe. This is a couple of years ago now, but it's work that we did more at the regional scale. And so for this particular work, we wanted to understand the importance of direct groundwater discharge to the water budget, to the Lake Simcoe water budget. And we wanted to, even beyond that, we just wanted to understand what field tools we could use to quantify direct groundwater discharge into these large lakes. Once we'd done this, we wanted to understand what's actually controlling the spatial variability in the direct groundwater discharge rates. And we wanted to also look at, there's a lot of regional scale groundwater models that have been developed in Ontario, often for source water protection planning, and they've been purpose built not to quantify direct ground or predict direct groundwater discharge, but we wanted to see if these models could be applied or what the utility was in using them to provide insights or kind of preliminary understanding of direct groundwater discharge into these lakes and the spatial variability. So this particular work was funded by Ontario MECP and was done together with 2 master's students. So there's a lot of different methods that are available to quantify groundwater discharge into lakes, as well as surface waters more generally. These include physical methods, chemical methods, as well as kind of modelling approaches. In this particular work, we used Radon 222, as well as using kind of those regional scale groundwater surface water models. So for those of you who aren't familiar with Radon 222, I'm going to talk about it a bit today. So to provide an introduction, Radon 222, it's a naturally occurring, and I'll say that again, it's naturally occurring radioactive isotopic tracer. And Radon 222, it comes from the uranium decay series. And often radon is orders of magnitude higher in concentrations in groundwater than it is in surface waters. And so when we see radon in surface waters, because it's it often is giving us a signature, it is giving us a signature of groundwater discharge. And this is because when that radon discharges into a surface water body, it's a conservative inert gas, which means it kind of evades into the atmosphere, and it also has a short half-life. So we can measure radon concentrations in the surface water. We can use mass balance models, and from this, we can back out and calculate what the groundwater discharge rates are. This is a tracer that's been really widely used in ocean environments, and now there's starting to be more of an uptick in its use in freshwater settings as well. So to use radon in kind of the large lake environment, we did boat surveys around about 200 kilometres of shoreline of Lake Simcoe, where we were continuously measuring the radon concentrations. So I spent a lot of time looking at the real estate on Lake Simcoe. But in addition to these boat surveys, we also had to do sampling to understand the radon concentrations in the groundwater M member for our mass balance models. So if we skip ahead to the results, here I have, so these kind of the colouring along the shoreline represents the direct groundwater discharge into the nearshore areas. So, you know, one of the things kind of I didn't mention at the start was that Lake Simcoe was a really neat place to do this study because you have very distinct geology around the lake. So you've got more sand and till plains in the south, and you've got shallow sediment and Paleozoic bedrock in the north. So we were wondering whether we were going to see any kind of regional patterns in the direct groundwater discharge rates. So we didn't see this, but you can see more that we had kind of high spatial variability, and you've got more of these localized groundwater discharge hotspots at different areas around the lakes. So we did find when we integrated this direct groundwater discharge that direct groundwater discharge kind of makes up around we estimated between 7 to 16% of the tributary inputs. So not a massive amount, but also not an insignificant amount, particularly when we consider this spatial variability and that there are some areas where we do have, you know, pretty high direct groundwater discharge rates. And so if there's groundwater contamination in those sources, they could be, you know, delivering fluxes to, you know, the lake bed kind of benthic communities as well as into the nearshore waters. So doing, you know, this sitting on a boat for 200 kilometres, not that I did it all, but it was really nice, but it was pretty resource intensive. So we wanted to understand kind of how could we, if we were to do this in the future, how could we better do preliminary screening to identify where we might expect to see areas with high direct groundwater discharge. So we looked at the hydrogeological controls. Was there any kind of where we're seeing these direct groundwater discharge hotspots? Was there certain hydrogeological features? So what we found is that we tended to have high direct groundwater discharge, as we'd expect, in areas where there was, you know, continuous high permeability, sufficient sediment near the shoreline. We found that we had high direct groundwater discharge in areas, particularly in the north of Lake Simcoe, where we're in close proximity to the Oro Moraine in the north, and there was we could see through the three-dimensional geological models that there was connectivity down to the lake. And then we also found the importance of the presence of, and this is probably the most prevalent one, was the importance of the tunnel channel deposits. So these are kind of where you've got erosional channels that have been infilled with higher permeability sediments. And so these are likely acting, you know, providing connectivity between deeper and shallow aquifer units. And where you have these intercepting the lake bed, we tended to see high direct groundwater discharge, except in the cases where you had kind of a stream incising through the tunnel channel deposit area. And so we saw this feature being important not only in Lake Simcoe, but also in work that we also did in Nottawasaga Bay and Lake Huron. So beyond understanding the kind of these hydrogeological controls, as I said, we wanted to compare our radon-derived groundwater discharge estimates with these regional scale groundwater models. And we knew they hadn't been purpose-built to simulate direct groundwater discharge, but we wanted to know if there was any utility in applying them for this purpose. So we had two different models that we kind of compared our results with, and we collaborated with EarthFX to use their models. So today I'm just going to talk about the model that was up in the Oro Hawkstone model, which was in the north of Lake Simcoe. And so here we can see a comparison between our direct groundwater discharge along the 45 kilometres of shoreline that the model covered and kind of the model output, the simulation output results from the regional scale model. And considering that the model wasn't purpose-built for this reason, we see a pretty good comparison between the results. Particularly in where they're identifying higher areas of direct groundwater discharge. We also see that, when we integrate across the 45 kilometres of shoreline, we see that they give a pretty good match with the total amount of direct groundwater discharge across that shoreline area. So this worked really well for the model in the north. We didn't have as good comparison for the model in the south, in the York area, because that model didn't have as fine, it was pretty coarse discretization. So it kind of showed us that while this approach may be possible, we do need to be careful with what models we're using to try to do this with. So we also use this model up in the Oro-Hawkstone area to do backward particle tracking, because this was really important to get an understanding of the legacy pathways. So if we want to be thinking not just about the groundwater discharge fluxes, but what that might mean for contaminant inputs to the lakes, it's important to understand, where was that groundwater originally recharging and what were the timescales. And while we didn't do it for this particular project, I think there is a lot of potential to kind of combine this backward particle tracking with legacy land use maps so that we can start to understand, okay, we have a groundwater discharge hotspot in that area. What was the land use, based on when the water was recharging? And it will give us an idea about what type of contaminants to expect in the direct groundwater discharge. So this is kind of where we ended it for this project, but we do currently have a new project that we recently started up. So this is with Jim Roy and Chris Power, and we're collaborating with the Oak Ridges Moraine Groundwater Program for all their great hydrogeological expertise to try and understand where we're getting hotspots of direct groundwater discharge into Lake Ontario around the GTA shoreline, and where this might be kind of aligned with high chloride inputs into the lake as well from the groundwater. So this work, we're combining geophysics as well with the radon, as well as the regional scale groundwater models. So this kind of, though, leads me on to the second area that I want to talk about today, and that's looking at, now I'm focusing on indirect groundwater discharge and the role of groundwater in delivering chloride into streams. So, as I'm sure many of you, are aware, the winter road salt de-icing is really causing not only, I think, in Waterloo, there is kind of acute challenges around its salinizing, wells that are being used for drinking water supply, but it's also leading to high concentrations of chloride in urban freshwater streams. And this is problematic because it causes ecosystem deterioration, as well as has been shown to kind of exacerbate other water quality challenges, such as eutrophication or release of metals. So there have been studies, however, that have shown that these chloride concentrations in streams are not only elevated during the winter when the road salts are being applied, but they're also elevated in the summer, and particularly during base flow conditions in the summer. So we know that under base flow conditions, groundwater is a major source of water into the stream. So a lot of previous studies have kind of inferred that this indicates the importance of groundwater, but there's really been no direct evidence of the contribution of groundwater to this fresh surface water salinization. So this is where we came in, and together with Jim Roy, we are co-supervising a student, Grant Hodgins, who's been trying to get this direct evidence and looking at it at the sub-watershed as well as the reach scale. So for this work, we've been doing work in a couple of different sub-watersheds, but I'm just going to show you data from one sub-watershed. This is a sub-watershed in London, Ontario. It's a mixed urban agricultural watershed where we have kind of a change in spatial geology across the sub-watershed. So for this sub-watershed, we've been doing work, so we've been doing work at that sub-watershed as well as the reach scale. And we know that in this stream, from continuous monitoring that we had down the stream, that more often than not, the chloride concentrations are above the chronic guideline limits for chloride. And we can see chloride concentrations, which I have, this is kind of over a 2-year period. The chloride concentrations, as we would expect, are higher in the winter, but you can see they're still elevated and above this red line, which is the chronic limit, during the summer as well. So We did work at the sub-watershed scale where we did longitudinal stream surveys. We were measuring radon, chloride, as well as measuring stream discharge for our radon mass balance. And then at the reach scale, we used a battery of different techniques to understand and kind of quantify chloride inputs into the stream from groundwater, as well as look at the exposure of the benthic zone species to these elevated groundwater chloride concentrations. So looking at the results from kind of the sub-watershed scale, so here what we did is we went down the stream. So this is kind of downstream, and we took radon samples at different locations down the stream on different days, and I'm just showing you the results here for like the non-salting, so kind of the summer season under base flow conditions. And so this is our groundwater discharge, estimated from our radon measurements as we kind of move down the stream. And here I have the kind of the chloride concentrations on all those same sampling days as we move downstream. I also show you here at the top where we move from kind of less permeability to higher permeability sediments, and when we move from more urban to more forest and agricultural kind of adjacent land use. So I'm just showing you this one as an example because it kind of nicely illustrates the data that we're getting. And so what we see is that as we move from kind of less permeable geology to higher permeable geology, we see an increase in the groundwater discharge rates, which is what we'd expect, more groundwater discharge when we've got this kind of higher when we move into the higher permeability area. We also see that because this is occurring in an urban area, we see a considerable increase in the stream chloride concentrations. So this is showing that impact that the groundwater discharge is having on the stream chloride. We do see, however, and so these concentrations, I've got these lines, this is the chronic guideline and this is the acute guideline. So we're well above those guideline limits in this stream. We also see, however, importantly, coming back to the point I made earlier, that the groundwater discharge isn't always making the chloride in the chloride stream problem worse, but when we have groundwater discharge occurring in an area which is forested and agricultural, we actually see a decrease in the chloride concentrations. So the cleaner groundwater is also improving the surface water quality as well down this stream. So we did work, as I said, at the reach scale as well, and our reach scale work was focused on this area where we have high groundwater discharge as well as high stream chloride concentrations, or an increase in the stream chloride concentrations. Here, I'm showing you the data that we got from pore water sampling, like stream bed pore water sampling that we did monthly over a 20-month period. And you can see that, and so this is along our reach, which is upstream as well as downstream of a major arterial road. So we can see that these pore water concentrations, so these are our concentrations 15 centimetres below the stream bed. We can see, again, they're much higher than our acute and chronic guidelines. And we can see the really high kind of spatial variability, like patchiness of these high chloride concentrations, which is, you know, what we frequently see with groundwater discharge. And we see that that kind of outweighs the spatial variability. So we're seeing kind of continuously, at certain locations, we're seeing continuously high chloride concentrations year round. And this is really important for understanding benthic, the exposure of the benthic organisms to these high chloride concentrations, because they're not getting any reprieve from these high chloride during the summertime. And these benthic organisms really play an important role in the food chain in the streams, and therefore the biodiversity in the streams as well. So we wanted to understand kind of, so this was looking at the chloride concentrations in the pore water, but we wanted to understand where is this chloride actually coming from. So we did different geophysical surveys. So we did electromagnetics. So this is kind of upstream of the road. We've got a large parking lot here where they pile snow. So we did electromagnetic surveys, as well as more detailed kind of three-dimensional electrical resistivity tomography surveys. And so these really nicely showed us that we have these high electrical conductivity or chloride plumes that are coming through the shallow groundwater towards the stream. And the nice thing about these surveys is you can get kind of vertical cross sections which provide a nice illustration of this. And I should note that we also ground truth this. We had boreholes and we did some well sampling as well. So we know that these differences we're seeing are due to the kind of the high electrical conductivity or high chloride groundwater rather than changes in the geology. So we're also able to, at the site, kind of along this transect here, do time-lapse electrical conductivity, electrical resistivity tomography surveys. And we can see just from like looking at this is over a 10-month period, we can see it just how persistent that groundwater, high chloride, high UC plume is in the subsurface and discharging to the stream. So just really explains why we're seeing these persistently high chloride concentrations during the stream. So although the road salts are only being applied in the winter, this is a year-round problem. So this work has really shown like multi-scale evidence of the impact of groundwater, not only on the stream water quality, but also on that kind of benthic zone exposure as well. So moving on to the third area I wanted to touch on, and this is work we've been doing looking at the impact of septic systems on surface water quality. So septic systems are often cited as, a key kind of source of groundwater contamination, but they can also lead to surface water contamination as well. So septic systems, for those of you not too familiar with them, they're widely used across Canada in rural and suburban areas where the households aren't connected to centralised wastewater treatment plants. We've estimated there's around 130,000 septic systems in the Lake Erie Basin. So septic systems are designed in their nature to treat wastewater and then disperse that wastewater into the subsurface. When this wastewater is dispersed through kind of a septic drainage field or tile beds, there's kind of concern that different wastewater contaminants of concern, including nutrients, emerging contaminants, pathogens, may contaminate the groundwater and also possibly contaminate surface waters as well. The great thing is, though, when septic systems are well functioning, is that you can get a high kind of degree of removal of these contaminants in the drainage field itself and in the unsaturated zone, which can limit the contamination of the groundwater and limit any potential transport into the surface water body. And so Will Robertson at Waterloo has done some incredibly great work on this over the last number of years, looking at kind of the attenuation of these contaminants in the subsurface down gradient of septic systems. Unfortunately, however, not all septic systems function as they should. And what does this mean, kind of underperforming septic systems? So when we think about underperforming septic systems with respect to surface water quality, this can mean a couple of things. It can mean that septic systems have been located in areas where they could have a high water table than they should, or a seasonally high water table, and you get the septic kind of subsurface contaminant plume being intercepted by drains, which basically short circuit those contaminants into a nearby surface water body. You can get septic systems where they get failure of that septic tile bed or drainage area. So it becomes clogged over time, and this can lead to breakout of the septic wastewater to the ground surface and then overland flow, particularly during wet weather conditions, into a nearby surface water body or kind of surface water or drainage ditch. In addition to this, although it's illegal, it is known that there are some households that have what are called direct pipes, hot pipes, straight pipes. There's a lot of names for them, but they're illegal. And it's where a homeowner has connected their septic system either up gradient or upstream or downstream of the septic tank directly to a surface water body. And this, of course, is problematic because it leads to rapid delivery of those wastewater contaminants into a nearby drainage ditch or into the surface water body itself. So over the last, 7 or so years, we've wanted to get an understanding of what are the importance of these, or relative contributions of these different pathways in delivering these septic wastewater contaminants into the surface water bodies, And then to try to start to upscale this work, we wanted to understand what percentage of septic effluent is actually reaching streams and how does this vary between different subwatersheds. So if you're in a low permeability subwatershed, vice versa high permeability watershed, or you're in an area with older homes versus newer homes, does this make a difference in how much septic effluent or wastewater is reaching the streams? So this work was done with 3 master's students who worked with me together with Jim Roy, and it was funded again by Ontario MECP. So for this work, again, we did this project at multiple scales. We did detailed, high-resolution stream sampling in 4 particular subwatersheds. We're really focused at targeting what are the pathways by which this septic wastewater is reaching streams. And then in addition to that, we did broad-scale field sampling across 53 different subwatersheds in the Lake Erie and Simcoe basins to understand how those different physical and socioeconomic characteristics might impact the performance of these septic systems and how much contaminant was reaching streams. So the 2 main traces that we used in this work, the first one is artificial sweeteners. So for those of you who aren't familiar with using artificial sweeteners, they're a really good tracer for human wastewater. This is because artificial sweeteners are ubiquitous in a lot of consumer products. So even if you're someone that tries to avoid artificial sweeteners, they're in personal care products as well. So they're often found in human wastewater. They're also very conservative in the environment, and they're mobile in groundwater as well. And then in addition to that, when we're measuring artificial sweetener concentrations in streams and groundwater, they're often above analytical detection limits. So when we see artificial sweeteners in the streams, because they're mobile in the groundwater and they're conservative, these sweeteners could have been reaching the streams by all of those different pathways that I just showed you. In addition to this, the other tracer that we used was HF183, which is a human-specific DNA source water tracking marker. And so HF183 is a microbial marker that's specific to human wastewater, and it's got limited mobility in groundwater or in the subsurface, a short half-life, which is why when we see HF183 in surface waters, it's indicating that we've got these rapid pathways associated with failing septic systems that are delivering that wastewater into the streams. So with these, now I'm just going to show you some of the results from kind of the smaller scale work we did, which was where we focused on 4 different subwatersheds. But I'm just going to show you an example data from one specific subwatershed, which I think really nicely illustrates kind of these different pathways that we're seeing. So this is some sampling that we did. This is just on a single day where we went down the stream and took samples from the stream and from any drains flowing into the stream under summer base flow conditions. So if we look at the results here I have the different artificial sweeteners on the y-axis, and I have the distance downstream on the x-axis. These are the artificial sweeteners, and we can also see those results along the stream for that DNA microbial source tracking marker as well, HF183 in black as well as E. coli. So what we see here is firstly, which was really interesting, is we see the HF183 concentrations are above kind of the limit that's often associated with human health risk associated with fecal contamination. So this is a concern, and having these high HF183 concentrations is indicating already that we've got these rapid pathways delivering the septic effluent into the stream. We saw really high kind of variability down the stream in these concentrations as well. And in particular, we saw kind of an increase in these human wastewater traces when we passed drains, and these drains had high kind of signatures of septic wastewater, so high sweetener concentrations and high concentrations of the DNA of HF183. But in addition to that, we saw really high increases as we crossed the road. So there's a road up here and another road down here. and our artificial sweeteners and HF183 really ticked up as we passed these roads. Now, along one of them, there was a drain, but there wasn't a drain at the other road. And so what this is indicating to us is really the important role that urban karst features are playing in short-circuiting septic effluent in the subsurface and delivering it into streams. So in these high permeability watersheds, for instance, you'd have utility trenches or subsurface infrastructure that's being put down roads, but around these are often gravel trenches. And so in low permeability areas, these can basically act as preferential flow paths and short circuit these contaminants into the surface water body, similar to what we're seeing here. So in addition to kind of this work we did at the small scale, we also, as I said, have done sampling around multiple sub-watersheds in the area. And for this work here, what I'm going to show you is the percentage of septic system effluent for these 53 different sub-watersheds. And so this has been calculated based on our measured acesulfame stream loads, so measured stream loads of the artificial sweeteners, and comparing this to what we know the number of septic systems upstream of our sampling points. So we see really high variability. So this is the log scale here, and we see high variability in kind of how much septic effluent is actually reaching the surface waters. Our master's students did some multi-level statistical modelling to show that generally we saw more septic effluent reaching the streams when we had higher flows, so higher stream flows, and that's kind of commensurate with the fact that we also see septic effluent reaching streams through drains, which are often running during wet weather conditions or, for instance, overland flow. We also see more septic effluent in the streams in sub-watersheds where we have older homes, which is what we'd expect, where we have more homes that are closer to the stream, and then finally also where we have a lower topographic wetness indicator. And this is often kind of is related to steeper topography. So, with this work and these results of this statistical modelling, we then had another student who was kind of a remote sensing, GIS, with remote sensing and GIS expertise, and he developed kind of a tool that we hope to be made available to practitioners and researchers that can not only provide or tell for certain areas, so here I'm just showing you for the whole Lake Erie Basin, but it can show how many septic systems are in a given area and then provide an estimate of how much, or a range in estimates of what the phosphorus loads are to surface waters from those septic systems in an area, and then the characteristics that kind of go into the calculations that we do. And so in using this particular online tool, as I said, here I'm just showing it for the Ontario Lake Erie Basin, but the user can kind of move around the map. They can select tertiary watersheds and get the information they need, quaternary watersheds and get the information, or they can just scroll around the map and it will automatically update to your area of interest about how many septic systems they are and what the possible phosphorus loadings are to the stream. So this work that we've done is the findings that we've provided, as well as these types of tools, are really important for trying to make science-informed decisions about, the design of septic systems, their maintenance, where they're located, as well as trying to inform septic system reinspection programs as well. And the work that we showed, in particular, that role of the urban karst and drains and short-circuiting contaminants into the stream is important for other groundwater contaminant sources as well, such as like leaky underground storage tanks and other contaminants kind of in addition to phosphorus, which we made this tool for. So, just in wrapping up, I have kind of a list here. There's a lot, as I said at the start, there's a lot of uncertainties around the impacts of groundwater on surface water quality in the Great Lakes. I have a list of them here. One of the things that I really haven't touched on is climate change and how climate change is going to change these groundwater surface water interactions, and affect the quality of aquatic habitats and affect, stream flows, and play a major role in this connectivity. But in addition to kind of these science needs, I really just want to call out what I think our challenge as a community is. We have such an incredible wealth of knowledge around groundwater science in Ontario, which really has stemmed back to Bob Farvolden and the leadership he provided in creating this kind of international research excellence in this area. But we as a community really need to do a better job at advocating for the role of groundwater and its impact on freshwater resources in Canada. Because at the moment, there's really poor integration of groundwater into freshwater resource science, management and policy, and really not a broad understanding amongst the freshwater management community about the really critical role groundwater plays as a drinking water supply, as well as for protecting the integrity of our surface water systems. So with kind of the last minute I have, I was at the Geo Montreal conference last month, and I just wanted to kind of bring to this audience the great work that had been done by some of the members out of the International Association of Hydrogeologists Canadian National Chapter, where they actually put forward a briefing that they submitted to the House of Commons Standing Committee on the Environment, Sustainability, Development, really advocating and pushing forward that the critical role that groundwater plays in effective freshwater management, and how we really, Canada's somewhere that's very surface water centric. We've got these incredible Great Lakes, so we forget about what's kind of beneath the ground. So in this particular briefing, they provided a number of recommendations, which I think we can all think about today. And one of them is terminology, so ensuring that in communication, in this particular case, they're talking about federal communication, but just generally in communications, when the term water is used, that it's encompassing both surface water and groundwater, and it's not just assumed that it's surface water. They had recommendations around monitoring and reporting, ensuring or kind of adding monitoring into the Canada Water Act, and getting kind of improved, meaningful, long-term groundwater monitoring of groundwater quantity and quality, so we can better understand kind of the long-term trends as we face these increasing human development and the changing climate. Their fourth recommendation was about inclusive forums and making sure that when there are kind of committees around freshwater management, that they always have groundwater experts at the table. Because groundwater isn't separate, it's not over there, but it is integrated completely into freshwater management. And then finally, education. And this is, I think, a piece that we can all play. And this is about educating the public and educating decision makers on the critical role that groundwater plays. And so I think that this is really something as a community that we can all kind of step forward and try to really advocate for the role of groundwater. And so these recommendations, if you're interested, they're available at this QR code here. So with that, I will end, and I would say I'm happy to answer any questions you have, but after saying it was a free-for-all, I'm not so sure anymore. So thank you.